Actually, when I pulled up to the hotel, well, first I'd like to thank my university for supporting me all these years. But when I first pulled up to the hotel, something beautiful happened to me. One of the students, Lily, had a card for me, a thank you card from last year, to thank me for having spoken last year at the EU. So I want to have a double dedication today, because as you know, I always dedicate my talks. And so I'd like to dedicate this talk first to the students, Lily, Catherine, Evgeny, Mohammed, and the others that I don't know, because of course the future does belong to the youth, and they bring the hope for science. And the second part of that, I'd also like to dedicate the talk to Don Scott, and because he's an example of perseverance, and I did really enjoy his talk on Birkeland currents. Whoops. I will figure this out. So we're going to talk about thermal emission, and these are the three fathers of thermal emission in my mind. Balfour Stewart. Now, Balfour Stewart is also one of the fathers of the gaseous sun. And Gustav Kirchhoff. Now, you know, some people think, well, gosh, Pierre, you're so hard on the poor Kirchhoff. Actually, you know, Kirchhoff was a brilliant man. We all make some progress, and sometimes we take a step back. So, of course, his laws of current are correct for voltage and current, and he's made enormous contributions to science. He's the father of spectroscopy. We must never forget that. Elements were first identified on the sun by Kirchhoff and Bunsen. So he's a giant in science. I know very little about Kirchhoff. The one thing I know is that when he was a very messy lecturer apparently, but he was very meticulous. Like he was very responsible. He always went to his lectures, except for one day. Apparently, he took the afternoon off, and that was the day that he got married. For those of you who know me, you know that I've been a great admirer of Max Planck. So it's a little bit of sadness that I give this talk. I've written this paper here on the life of some aspects of the philosophical works of Max Planck. I don't think people read these books too much, but I would encourage you that if you get a chance to read his philosophical works, I think Max Planck had a lot to contribute to the philosophy of science. And just right off the bat, I want to say that some people have accused me that I don't believe in Planck's equation. Well, that's not true. Planck's equation is correct within an actual black body. The question for us here is, do all cavities actually contain black radiation? Sorry. Okay, that's the one I want. So as we know, all objects emit light. My son was with me this year, so he made me my slide. And so early black bodies were coated with paint and black soot. And they were the best absorbers of heat radiation and also the best emitters. So, you know, when scientists like Leslie with his cube started understanding heat radiation, you know, they painted the cube one surface with soot and another surface with something else, and then they noticed that soot was a very good absorber. So the problem that we want to deal with here are modern black bodies, and they're actually cavities. Now, in the laboratory, they're very complex things. I mean, our government spends many, many thousands of dollars building good black bodies. And it's a science that's existed a long time. Black bodies are used to calibrate all kinds of things. But one thing is always true is, first, they're heated. They tend to be heated sources. And secondly, their interior is lined with highly absorbing materials. These are two papers that I wrote quite a while ago now. And they're worth looking at just to see the history of black bodies. The second one is critical, of course, of Kirchhoff's law, and the first one talks about Planck's constant need to put a carbon particle in his work on black body radiation. Why do we care? Why is Pierre talking to us about black bodies? Well, if I try to explain it to you simply, a proper understanding of black body radiation is important as it touches virtually all aspects of physics, from the study of condensed matter to the understanding of noise power in NMR, my own discipline, and to fundamental astronomy. Everything is linked to black body radiation. Many, many things, I will say. So of course, as you know, this is the most famous thermal spectrum. Notice I didn't say it was a black body spectrum. It looks like a black body spectrum, but it's actually a thermal spectrum. And why don't I say that it's a black body spectrum? And because first of all, well, there's a couple of points to make. A gaseous sun could never produce this kind of spectrum. It can only do so if Kirchhoff's law was valid. What Eddington argued is that the center of the sun was very hot, millions of degrees, and according to Stefan's law, you would get an enormous amount of photons coming out of the center because it's temperature to the fourth. And then he thought the outside of the sun was at 5,000, so 5,000 to the fourth is nothing like 15 million to the fourth. So he saw the sun as essentially enclosed. So because it was essentially enclosed, most of the photons stayed inside and the sun was leaking like a slowly leaking sieve. He felt that it was enclosed. But actually, he had no right to apply these equations to the sun, since the surface of the sun does not meet the requirements for a black body. What is the requirement? You have to have rigid enclosure with no conduction or convection currents, and therefore you can never get a true black body spectrum. The sun has a thermal appearance, but it only provides us an apparent temperature. This is not a real temperature. It's giving us some insight about the vibrational degrees of freedom of the lattice of the photosphere. It's telling us, I have a lattice. That's even more important. We know the sun has a lattice because of this spectrum. It must be condensed matter. The sun, remember, the sun's surface can produce X-rays, and that manifests temperatures and energies in the millions of degrees. And we have to remember that the sun maintains its energy in conduction bands and its convection currents. Now on this, On this, Max Planck has some very important caution in his book. In section 51 of the Theory of Heat Radiation, he says, and I think I've quoted this here before, now the apparent temperature of the sun, this 5,000 degrees, is obviously nothing but the temperature of the solar rays and depends entirely on the nature of the rays, and hence is the property of the rays and not a property of the sun itself. Therefore, it would be not only more convenient, but also more correct to apply this notation directly instead of speaking of a fictitious temperature of the sun, which can be made to have meaning only by the introduction of an assumption that does not hold in reality. He's telling us, don't go set 5,000 Kelvin for the surface. We've done it for 100 years now, more than 100 years. I'm sorry. Well, what's the second most famous thermal spectrum? Well, it's the microwave background. And astronomers, when they found it, they were pretty enthused. They said, wow, we have a nearly perfect black body eventually by the Kobe team with this phenomenal temperature of 2.725 plus or minus 0.002 Kelvin. And the question is, are we allowed to take this temperature? Kirchhoff's law tells us that to get a valid temperature, so if you believe in Kirchhoff's law, what is the requirement? First, the universe is not contained in a rigid enclosure. So that's why cosmologists, at the very, very beginning of the Big Bang, they desperately want equilibrium. There was a moment there in their mathematics, or however they want to create it, that in this moment, we had thermal equilibrium. Because without thermal equilibrium, they feel that they could never get the black body spectrum. But the Big Bang is a non-equilibrium process by definition. There was never thermal equilibrium with an enclosure as required by Kirchhoff's law, even if the law was valid. And the second point is that on Earth, a black body spectrum requires the presence of a vibrational lattice. We build black bodies from solids. Water is known to be an excellent absorber of microwaves. That's important. When Penzias and Wilson published their paper, there's no mention of water. Nobody discussed the fact, where's the signal from the Earth? Since water is a powerful absorbent of microwaves, it must be a powerful emitter. Where's the microwave spectrum from the Earth? It had to interfere with Penzias and Wilson's signal. They're sitting on the Earth. And of course, my mother did have a microwave oven. Now, they say, well, we have a monopole, so we know that this monopole exists, and this is our proof that we have the microwave background. But here's the thing, the monopole has never been detected at L2. This is the position of WMAP and the Planck satellite. All CMB anisotropy maps and polarization maps are devoid of scientific meaning. There is no science in these maps. Why? First, there's no cosmological science in these maps. First, they lack cosmological stability. So if you look at the WMAP data from year 1 and the 3-year average, the next set of papers, when they were actually showing us what they were doing, you can see that there's no stability in the maps. It's all over the place. They're changing the coefficients by a factor of 100 when they're combining the maps. So they don't have cosmological stability. Therefore, this has nothing to do with cosmology. It's also impossible to remove the galactic foreground and the foreground polarization. We've known for 100 years that the galaxy emits some polarized light. You can't get around it. You're in the galaxy, and you can't see through it. An infinite number of so you cannot subtract the galaxy out so that you can see what's behind it. No more than I can take this wall out to look at somebody in the next room. That wall is in front of us, just like their galaxy is. The other problem is an infinite number of anisotropy maps is possible, as only normalization is required. If you don't believe me, look at the WMAP maps, and then look at the maps from Dr. Tegmark. They're completely different maps because he processed them a different way. We can all process our own maps. The inversion of image data is open to violation of thermodynamics, possibly generating negative temperatures, which are forbidden in this context. That's a point I made last year. So these are all the reasons why black body radiation is so important. It's the beginning of the mathematics of a gaseous sun. You must have Kirchhoff's law to be valid in order to have a gaseous sun. Kirchhoff's law is also important because you must have it in order for the Big Bang to give us that thermal spectrum. And so that's why, for me, it's all about Kirchhoff's law. Now, there is a law, which is a proper law, called the Law of Equivalence. It comes from Stewart. I talked about it last year. He wrote the law this way. The absorption of a plate equals its radiation, and that for every description of heat. That's when you have no other processes. You only have radiation. There can be no conduction, no convection. If that's true, then these statements are true. He also worded it this way. The absorption of a particle is equal to its radiation, and that for every description of heat. So now we get to what Kirchhoff did. Now, as you know, the laws of physics come from experiments. We do experiments, then we make laws, because the experiments tell us the facts. Sometimes people don't quite understand this about science. We gather facts first. From these facts, we make laws. And from the laws, we make theories. So if you want to question a theory, you have to make sure that laws exist. and you have to have your facts right. So Kirchhoff made Kirchhoff's law, and if you read the paper, what is flagrantly absent from the entire paper is any experiment. This is very different than Stewart's paper. He does talk about the turbulent plate, but this has nothing to do with the formulation of Kirchhoff's law itself. So Kirchhoff's paper talks completely about a theoretical move to a law of physics. That is a violation. Now, when he starts, he says, this investigation will be much simplified if we imagine the enclosure to be composed, wholly or in part, of bodies which, for infinitely small thickness, completely absorb all rays that fall upon them. So he sees something black as something that it's very thin and it'll absorb all the rays right away. Now try to remember this, because later in the talk you'll see how Planck has completely changed the definition of a black body. So for Kirchhoff, their black bodies, their walls have infinite small thicknesses which completely absorb all the rays which fall upon them. And here's his claim, which people have risen to a law. And this is what he said. When a space is surrounded by bodies of the same temperature, and no rays can penetrate through these bodies, every pencil in the interior of the space is so constituted with respect to its quality and intensity as if it proceeded from a perfectly black body of the same temperature, and is therefore independent of the nature and the form of the bodies, and only dependent by its temperature. In the interior of an opaque, glowing, hollow body of a given temperature, there is consequently always the same brightness, whatever the nature may be in other respects. And this was completely false. This was never shown in arbitrary cavities. Remember, Kirchhoff is applying this to all cavities. If you have an enclosure, inside you always have black radiation. This is what he's telling us. He's telling us this theoretically, but in experimental reality, it was never true. So here's a summary of his law. The ratio of the emissive power and the absorptive power is the same for all bodies at the same temperature. So he then immediately sets the absorptive power to 1 so that he preserves units. So you're going to have units for emissive power, and that's going to be the function E. And that function E is Planck's equation. And as I mentioned before, in a real black body, things that are made from good absorbers, that function E is known, and Planck, thank God, gave it to us. So for Planck, he had a very, very different view of a black body, and this is where the danger begins. For Planck, black bodies consisted of enclosures made of perfectly reflecting walls. Just read his book. You'll see the whole book is on perfectly reflecting walls. And in this setting, he always placed a little piece of carbon. Everywhere, and you could read my paper, Black Body Radiation and the Carbon Particle, where I talk about Planck's constant introduction of a carbon particle. Well, what is a carbon particle? It's a perfect absorber. But his perfectly reflecting walls can't produce any photons. They're perfectly reflecting. So he wrote in his book, it is therefore possible to change a perfectly arbitrary radiation which exists at the start of an evacuated cavity with perfectly reflecting walls under consideration into black radiation by the introduction of a minute particle of carbon. Now, to me, he had no right to put the carbon in there. If all cavities are black, why do we need the carbon piece? Now, there's several presentations of Kirchhoff's law. I showed you Kirchhoff's, the emissive power divided by the absorptive power equals the function of Planck. Planck, unfortunately, uses the symbol for emission coefficient divided by the absorptive coefficient is equal to the specific intensity. And actually, you have to multiply this by k squared, the velocity of propagation. And then the modern notation is just the emissive power divided by the absorptivity is equal to some function of temperature and frequency and the index of refraction. Now, before we proceed too much with blackbody radiation, I want to recall to people what Stewart's law says. Stewart's law says that the emissivity is equal to the absorptivity, but that only holds when there's no conduction or convection present. So there's such a thing as dead blacks, and they're used in the experimental setting. And what happens is you can have geometric effects when you have conductive or convective paths that are open. So what happens is the photon comes in, and you have this horn, okay? And the photon just gets trapped in the horn, and the energy is dissipated by conduction. So measuring reflectance, so people sometimes they say, well, how black is this cavity that I have? So what they do is they irradiate it with blackbody radiation. They're testing another, so they have a standard, and then they want to test this cavity, so they irradiate it with light, and they want to see how much light comes back. Well, the problem is that's a very, very dangerous thing to do, because if you have conductive paths out, as a dead black will show us, then you're going to get the wrong answer. Now, some of you guys might know that I have a degree in zoology too. So we'll go to the monarch butterfly. And the monarch butterfly is extremely interesting. There's a professor at the University of North Carolina who wrote, if you ask me, what is the blackest thing you've ever seen, I would say it's the black on a monarch. It's just dead black. And it is that way not because it's a dye, but because of the nanostructure that gives it that property. So what happens is that the butterfly, and it's actually dead black also in the infrared. So if you take a monarch butterfly and you had an infrared camera and you put it on some milkweed and you took a picture, the milkweed will be very bright, white looking. And that's because it's reflecting infrared from the environment. But the monarch, the black part of the wing, will still be black. What is that telling you? The monarch is absorbing the photons. It's a dead black. It's absorbing the photons and doesn't want to give any out. Now, why is this important? Well, in the Planck satellite, there are things called the 4 Kelvin loads. They're 4 Kelvin reference loads. This is critical to the functioning of the LFI of the Planck satellite. Well, how did they build it? They built the load, and then they put conductive washers to the 4 Kelvin shield to make sure that this thing stays at 4 Kelvin. So what did they introduce? They introduced a conductive path for heat outside of a black body. It doesn't need to emit photons. So if anybody asks me, oh my God, the Planck satellite, it's getting all these things. Its LFI is not even properly designed. Now, Stewart came close to doing something like Kirchhoff. He almost said all cavities contain black radiation. But the difference is Stewart never made it a law. He knew that mathematically things could tend towards black radiation. So he wrote this principle, never making it a law. Let us suppose that we have an enclosure whose walls are of any shape or any variety of substances, uniform at all temperatures. Okay, sounds like Kirchhoff. But this is before Kirchhoff. The normal and statistical condition will be that the heat radiated and reflected together. Radiated and reflected. So now reflection comes in. Which leaves any portion of the surface shall be equal to the radiated heat which would have left that same portion or surface if it had been composed of lamp black. So just as if it had been lamp black. Let us suppose, for instance, that the walls of this enclosure were polished metal. Then only a very small quantity of heat would be radiated. But this heat would be banded backwards and forwards between the surfaces until the total amount of radiation radiated and reflected together became equal to that of lamp black. So this is what he's proposing here. So in a cavity that's actually a black body, on the left, you see the emissivity is 1, and you get the proper emission. Now what you do with low cavity emissivity, low emissivity cavities, like let's say the emissivity is just 0.1, now you'll get, if you keep heating this cavity, you're going to keep getting photons produced until eventually you could try to fill the cavity with blackbody radiation, okay? So with heat added, what's the problem with low emissivity cavities? Well, if you try to do this with a silver cavity, the problem is if you try to heat the wall of the cavity, what is it going to do? Is it just going to keep emitting photons until it fills the cavity with black radiation? Of course not. It's going to change its temperature. You won't be able to control it. The wall temperature is going to go up. It doesn't work. So Stewart's principle was a mathematical argument. He had no experiments for this. Now, if you look at Devois's papers, and these are true classics in heat radiation, the citations are below. Devois argues, by changing the dimension of the cavities, we can make them appear more black. Well, of course, that's the dead black problem again. They appear more black. You're sending radiation into it, you make it big, and it looks like it's absorbing it. But this demonstrates that Kirchhoff's law was never valid, as dimension must only be determined by diffraction consideration. It's not the emissivity. You can't say, well, this has a lower emissivity, so let's make it really big so that it works. I don't name people, but there was a fellow of the Royal Society of Engineering that told me in an email, generally, I'm paraphrasing from him, the reason we do not make cavities from low emissivity materials is that they would be too large. Well, I'm sorry. This explains that Kirchhoff's law is not valid. You have to be able to make the cavity from a low emissivity material. That's what the law says. Now, Planck did look at the two-cavity problem, and this is treated in the paper by Steve and I. And so he imagined that you had a cavity, and these are perfectly reflective walls. You see the emissivity is 0, rho is 1, so it's perfectly reflecting. So we start on your left, where the little carbon particle is. So he says, well, in that cavity, which is perfectly reflecting, inside there's radiation. And there's a stopcock. The opening is not opened yet. And he says, well, now, to make sure it's black radiation, I'm going to put a little piece of graphite in there again. Okay? And then he says, let's open the stopcock. And when he opens it, he permits the photons to flow to the right. And he says, well, what's going to happen is the temperature of this system will drop by the change in the volume. But there's two arguments with this that are completely wrong. First, if Planck believes in Kirchhoff's law, both of these cavities had to be filled with black radiation, so who cares if you open the stopcock? How do you get that equation? So if Kirchhoff is right, that both cavities contain black radiation, then this relationship cannot be right. Or, I'm right, this is a perfect reflector, and Planck says that you can dismiss the graphite particle. So we'll pretend as if it's not there. So if it's a perfect reflector, and there's nothing to produce heat radiation inside these reflectors, then the cavities are empty. So you can never get this drop in temperature. Now, the more interesting problem is one I've dealt with last year, and actually this problem is so interesting that it's going to be the source of my next paper, and that's going to be you have emissivity, a cavity which can emit on the left, and a cavity that does not emit on the right, and then you open the stopcock and see what happens between them. The question is, did the cavity on the right have black radiation? And when we open it, does both of these cavities become filled with black radiation, or is something else happening? The one clue I'll give you is that the cavity on the right, because it's got zero emissivity, that means that it has its energy in conduction bands, and they have a chemical potential, and that's an important part of this problem. So this has to be revisited, even though I did speak about it last year. Whoops. So now we're going to deal with Planck's derivation of Kirchhoff's law. And this is extremely important because in the beginning of Planck's book, the first 51 sections have to do with the derivation of Kirchhoff's law. And the central part of this talk is to show that Planck's derivation is not valid at all. So in English, The book is called The Theory of Heat Radiation, and you can get it online. And for people who really care about the translation, you can find an English and German translation of the Theory of Heat Radiation in the History of Modern Physics, and the citation is there. So if you don't like how the translator translated and you could read German, then you could go ahead and make sure that the translator did it correctly. I do want to acknowledge Steve. Steve and I got together on this problem. You know, I changed my cell phone plan this year so that, you know, Steve and I can call. And it cost me nothing to call to Australia, so sometimes we talk quite a while. And when we started talking about this, we spent 4.5 hours on the phone. And then finally I decided, well, it's time for me to go see him. So in the preface of the Theory of Heat Radiation, Planck writes that he deviated frequently from customary and frequent treatments of Kirchhoff's law, of customary and frequent methods, wherever the matter presented or the considerations regarding the form of the presentation seemed to call for it. And he notes, I deviated especially in the treatment of Kirchhoff's law. Now I want to point out to you that there is, and anyone who finds a proper theoretical proof of Kirchhoff's law can give it to me. People have said mathematics is the language of physics. Well, if you don't have a theoretical proof of Kirchhoff's law, I guess you don't have a law. So it takes two things, right? You have to have the facts, you summarize it in the law, and then we need the mathematics to show that the law is valid. And what we're showing here is that the mathematics that Planck used was not correct. So in deriving Kirchhoff's law, Max Planck considers the radiation which he believed existed within an object. So Planck moves his mind inside a material. That's very important. But heat transfer within objects usually takes place with conduction, phonons, conduction bands. And if there's a liquid or a gaseous state, we also have convection. This observation is sufficient to discount Kirchhoff's entire proof because he's got photons moving inside the object. However, for the sake of revisiting this time period, we'll just pretend that yes, we can have photons within an object, and that in order to expose that Kirchhoff's law has no theoretical foundation, and we'll assume, as Planck does, that heat exchanges internally within an object by radiation. Sorry. Okay, so this is Planck's setting. He considers a volume element of the center V and a point at the edge of this circle defined by R, O is the origin, and he's looking at the exchange of radiation between them. So what he writes is that he equates the volume element emissive and absorptive power. So on the left, we have the emissive power. On the right, we have the absorptive power. Now, I should note here that for Planck, epsilon sub nu is the emissive power E of Kirchhoff, okay? So even though he calls it the coefficient of emissivity, he's actually referring to the emissive power. So he gets this equation. It leads to his equation 27. So he considers only emission and absorption problem, and he leads to equation 27, which will soon lead to Kirchhoff's law. So Planck did not include reflection in his derivation, as the effect actually can cancel out in this case. So if I include reflection, you can see on the left equation now I've added a term, rho times the specific intensity, and on the right I've added rho times the specific intensity too. So I've added the reflection. Now, it can lead to one of two things. If you solve this equation, you can get Planck's equation, of course, emissive. And by the way, in my case here, I'm using Planck's notation. So again, epsilon sub nu is not, even though Planck calls it the coefficient of emission, it's actually the emissive power. And so now what you have here is, you have again, from this equation, you can cancel out the rho terms and you'll get Planck's equation. Or you can recognize that alpha plus rho equals 1, And then in that case, you're going to end up getting another equation. It's different. Both of these equations come from this form. And now you can see that in this case now, all of a sudden reflectivity becomes part of the problem. So in Planck's derivation, reflectivity is gone. Now we bring it back in. So it's a warning. Now, what is the proper equation to use? Well, any mathematician will tell you that you don't use equations that can ever be undefined. The equation on the left is undefined if alpha goes to 0, right? That blows up. So this is undefined, whereas the equation on the right is never undefined. But Planck steered himself to the equation on the left, whereas the equation on the right was more prudent. Whoops, I'm sorry. So in order to get Kirchhoff's law, Planck must show that it's independent of the nature of the substance used to make the cavity. So this is the equation he actually wants, is that the velocity of propagation squared times the specific intensity of medium 1 is equal to the velocity of propagation squared times the specific intensity of medium 2. That's what he wants. Now let's see how he gets there. The first thing is he treats black body radiation in a very different way than Kirchhoff does. First, he says, let the specific intensity of radiation of frequency V polarized in an arbitrary plane kV in the first substance, and then kV in the second substance. So he's kV prime in the second substance. So he's now moving towards polarized light. That's very dangerous. And I'll explain to you why in a minute. Black body radiation is never polarized by radiation. Planck knows this. He writes later on, for a plane wave, even though it be periodic with waves lying within the optical or thermal spectrum, can never be interpreted as heat radiation. So the whole proof of Kirchhoff's law will depend on Planck's use of polarized radiation. But polarized radiation has no place in the derivation of Kirchhoff's law because black body radiation is never polarized by definition. Whoops, I'm sorry. So Planck then redefines the black body. Remember when Kirchhoff was saying very thin? Absorbs over a thin layer. So in addition to black surfaces, the term black body is also used. This is quoting from Planck. According to Kirchhoff, it denotes a body that has the property of allowing all incident rays which enter the surface, which enter without surface reflection, and allowing them to leave again. Okay? So then he makes a footnote. He says, in defining black body radiation, Kirchhoff assumes that the absorption of incident rays takes place in a layer infinitely thin. What does he do? We do not use this in our definition. So Planck moves away from the classic definition of black body radiation. What does he do? He says a black body is a rough surface having the property of completely transmitting the incident radiation, and it's now described as black. Now, transmission has no role in black body radiation. Black bodies are always opaque, but Planck, for his mathematics, needs to use transmission. So now he defines the black body as completely transmitting the radiation into the body. Then he goes further. Strictly speaking, the surface of a body never emits rays. Okay, that's a new one. But rather, it allows part of the rays coming from the interior to pass through. The other part is reflected inward according to the fraction transmitted. As larger or smaller, the surface seems to emit more or less intense radiation. So he talks about the surface as permitting radiation to come out of the body and permitting radiation to be transmitted into the body. Now, to properly understand radiation, the correct expression is that this vector 1, you have a photon and it's coming through a surface. There's two media here, and there's two things that can happen. Three things that can happen. Some of the energy can be absorbed and then re-emitted. That's the term alpha. It's the absorption. It's also equal to the emission. So alpha equals epsilon v nu. So this is the same term. I'm accounting for it in the correct expression. Then we have that some of the radiation can be reflected. That's the rho term. And then we also have some of it can be diffracted into the second medium. That's tau. But what Planck ends up using is the bottom expression. 1 equals rho plus tau. Alpha is not in it. And that's a violation. He cannot ignore alpha. Elsewhere in his book, he says that when you have black radiation, you always get a little absorption of the light for every path traversed. For every point along the path traversed, you get a little bit of absorption and re-emission. He knows it, but in his derivation of Kirchhoff's law, he removes it. So now, we look at Planck's setting. Now, this is one of his figures in his book, and I've just expanded the figure so we could better understand it. On the left, we have two media. So now Planck takes two arbitrary media. We're going to take two arbitrary materials and we're going to put them together, okay? And now he's going to end up showing that Kirchhoff's law is valid by doing this. Two arbitrary materials, put them together. So he has specific intensity, K sub nu on the left side. You'll see K sub nu in the left figure on the upper right. And so now you have specific intensity coming towards the surface. Some of it is reflected, and some of it is diffracted into the second medium. And then in the second case, you also have, there's some radiation that's coming K prime sub nu in the lower right of the second half of the figure, and that's coming towards the first medium, and some of it is reflected, and some of it is diffracted into the second medium. Now, after a lot of playing, So after a lot of playing, Planck arrives at this equation. Now remember, what does he want? He wants K sub nu times Q squared equals K prime sub nu times Q prime squared. So if the term on the right was gone, you could see you could just move the denominator on the left to the right, and you'd have Planck's equation. Now, how do you get that? Well, you need to remove those rows. Now, what are those rows? Well, that's reflectivity. Planck needs to show that reflectivity is 0. If he could just set that reflectivity to 0, rho prime and rho to 0, then you have 1 over 1, which is just 1, and you move the bottom denominator, the denominator on the left to the right as the numerator, and now you'd get Kirchhoff's law. So that's what he needs. So now he needs to get rid of those rows. So what does he do? And this is the violation. He then considers only plain polarized light. And then he sends the light at Brewster's angle. So he knows that if you send light from medium 1 into medium 2, and you happen to send it for a certain frequency at a particular angle called Brewster's angle, some of the light, now with the little dots here, they're showing light, the two directions of light, they're perpendicular to one another. So we got two planes perpendicular to one another. The light is moving, and we're considering both planes of polarization. So the dots are coming towards me, in and out of the plane, and the little arrows are in the plane of the slide. So what does Planck do? He sends the light at Brewster's angle, okay? And then some of it, the part that will be diffracted, you'll get both components in there. But the part that will be reflected, you will only get one of the components that's reflected. So what does Planck do? He says, well, look, I'm going to use polarized light for my proof, and I'm going to only use the little arrows. I'm going to send polarized light, and it's going to be polarized like the little arrows. So, of course, nothing will be reflected in the upper left left quadrant of the slide, right? That, where it says first medium there, that arrow will be gone, right? Because Planck, when he does the test, he now uses polarized light, and it's only the little arrows that are coming in, so everything will come, the little arrows will only be diffracted, and the upper right quadrant will be empty. That's a violation. Why? Because first of all, he's not allowed to use Brewster's angle, and secondly, he's dealing with heat radiation. He's not allowed to use polarized light. So then, and it's hard for me to criticize Max Planck, because remember, I've read his writings. So Planck infers the general case. He now states that if I use polarized light, I can prove that rho equals rho prime equals 0. Well, why? Because he used polarized light. So now he gets this equation 40. All you guys can go look it up. In his book, this is equation 40. Rho equals rho prime. Well, as Steve will tell you, rho does not equal rho prime. And as I will tell you, in Planck's world, there are no colors. Because why do we have colors? Because things have different reflectivities. But now Planck has just proved by taking two arbitrary materials that these two materials will have the same reflectivity. That is contrary to all known experimental and observational physics. So setting rho equals rho prime, Planck finally is able to remove the rhos from this equation and get Kirchhoff's law on the right. So he sets rho equals rho prime. There are no colors. He gets Kirchhoff's law. But had he properly treated absorption, remember how he started this? There's no absorption. Well, we're talking about black body radiation here. The whole thing is about absorption. How could you not treat it? If you properly treat it, this is the equation that you get. Now it's not just 1 minus rho prime, but it's 1 minus rho prime minus alpha prime. Well, you can never, ever make this come to Kirchhoff's law. You can never ignore the absorption. So what's the conclusion? A valid theoretical proof of Kirchhoff's law does not exist. There is no theoretical proof of Kirchhoff's law. You'll find that in the paper that I wrote with Steve. And Schirmacher, in 2003, actually wrote about the proofs of Kirchhoff's law before and after Planck. And if you read this paper, you'll come to understand there are no proofs of Kirchhoff's law. He ends by saying, in this paper, he ends by saying that Einstein removed the ladder on which Planck had climbed. Oh no, I'm sorry. Kirchhoff's law, Einstein did not remove. Planck, because Einstein never derived Kirchhoff's law. He derives Planck's equation. Okay? And so Planck had, and why do we want Kirchhoff's law? So I said Planck's equation is valid. Einstein's derivation of Planck's equation is very elegant. He uses a Wien's field, introduces it, and he just gets it from Einstein coefficients, and bam, Planck's equation falls out. So I don't have a problem with Planck's formulation of his equation. I have a problem with saying that equation is universal, that all cavities, including the sun and the Big Bang, have to have black body radiation. That is simply not true. Now, most people think Planck wanted his equation. For him, that was the gem. That was the gold ring to get the equation for black body radiation. But that's short-sighted. That's not really what Planck wanted. He wanted universality. And here it is. With the aid of the constants. So Planck had no theoretical basis for invoking universal constants. And what did he say? He wanted things to be universal, that his equation would apply everywhere. With the aid of the two constants, h bar and k, which appear in the universal law of radiation, we have the means of establishing units of length, mass, time, and temperature. So you talk to the cosmology, there's Planck lengths, Planck time, Planck temperature, Planck mass. which are independent of the special bodies or substances, which necessarily retain their significance for all time and all environments, terrestrial and human and otherwise, and which may therefore be described as natural units. And he says, the quantities will retain their natural significance as long as the laws of gravitation and that of the propagation of light and vacuum and the two principles of thermodynamics remains valid. So Planck gives us these two constants, H and K, and he says a Martian out there or some great creature far, far away for the Star Trek lovers, they also get to derive Kirchhoff from blackbody radiation. They'll also get to derive Planck's constant and Boltzmann's constant. And what I'm telling you is that when Kirchhoff's law collapses, those constants lose universal significance. Planck's constant and Boltzmann's constant have no more significance than the mile versus the kilometer has, right? We define them. We found these constants by the experiments we made and the restrictions that we put on that setting. Does experimental proof? So now I've told you there's no theoretical proof. Anyone who has a theoretical proof of Kirchhoff's law, send it to me. I've been looking. Does an experimental proof exist? Because after all, experiments define the laws of physics. So, well, maybe Kirchhoff didn't have the math right, but maybe there's an experimental proof exists. Remember, Kirchhoff's classic paper was theoretical in nature. It contained no experimental proof. So the question is, do arbitrary cavities contain black radiation? No, it's not even close. Laboratory black bodies are always made from good absorbers of radiation. They're never made from poor emitters. Graphite and soot continue to play an important role in their construction. Planck's equation remains unlinked to the physical world. So what is happening in physics? You have one of the most important equations in physics, and it's unlinked to physical reality. Why? Because Planck couldn't link it. Kirchhoff had said this is independent of the nature of the walls. So because it's independent of the nature of the walls, you can't look for a physical mechanism. You can't say, well, in this wall type, this is how a photon comes out. Okay? So Planck's equation is unlinked to the physical world. Well, isn't that great for cosmology, for astronomy? Anything can give you a black body spectrum. The Big Bang can give you, a gaseous star can give you one. But guess what? In our laboratories, if we want to have one, we spend millions of dollars and we use graphite and very complicated devices. We don't just build cardboard boxes. So the question for me is, and this is the fundamental question for physics, which Einstein tried to answer, and he never answered it. I think he spent like 5 years trying to understand, why do you get a photon from a solid? Why is it that graphite emits a black body spectrum? So people who are out there trying to understand the universe, I don't want to know. I just want to know, why does graphite give us a photon? Where does that photon come from? What is the physical setting? What are the energy levels? And what is the transition species? And when condensed matter physics answers these questions, modern astronomy will collapse. Because once you answer this in graphite, guess what? The sun will have to use the same mechanism. And everything else that we think is giving a thermal spectrum. So Planck remains unlinked to the physical world. Whatever mechanism is eventually invoked in graphite must also be present in the solar spectrum and the microwave background. That is why a gaseous sun cannot survive if Kirchhoff's law is found to be invalid and if Planck's equation is finally linked to the physical world. That is also why the microwave background never came from a cosmic source like the Big Bang. Because whatever mechanism is used in graphite to emit a thermal spectrum was never present in a primordial atom. And then I'm going to leave you with this little slide. This is the experiment of Rubens. This was done at the time of Planck. So on the left, you have a black body there with electricity coming in, and it's filling a glowing coil. And then you have plates permitting the radiation to come out. And this is hitting a bunch of crystals, and then a mirror. The crystals are in blue, and then a mirror. And then finally, there's a thermocouple on the right. It looks like a pencil, okay? So what is happening here? This is called the method of residual rays. What Rubens was doing is he had too much radiation, so every time you hit a crystal, some of the radiation is transmitted, is diffracted away, and so you can get rid of the residual rays of the extra. You can preserve the residual rays and get rid of the contamination. What contamination? This is supposed to be a black body. So in closing, of course, I'd like to thank Steve for his friendship and his assistance in this. My son Luke, he's my artist. If you look at all my papers, Luke did the work on the art. I can't draw very well. And the pictures of Kirchhoff, Stewart, and Planck have been drawn by Bernadette Carstensen. You might Google her name. She's a phenomenal artist. She did these for me kind of as a favor. But if you want to see some beautiful art, look at Bernadette's art. And I also like to thank the editors of Progress in Physics. And when we define courage, we can put Dmitry in that company that he started his journal. And if you knew Dmitry's living conditions in Russia, you would understand what I mean. Thank you very much.